Hello everyone. In this lecture, we are going to cover the continuous probability distribution. And in continuous probability distribution, the most important is normal probability distribution. So let's find out what we have in this lecture. We're going to recall few of our terms that we have already covered in our previous lectures, and then we're going to discuss about normal distribution, normal curve and its characteristics, area under the normal curve, and at the end the exponential distribution. As you know that distribution of the probabilities among different values of a random variable is defined into two categories. One is discrete, another one is continuous, according to our random variable x. So let's see some examples of continuous random variable like weight, height, temperature recorded by the meteorological office, time to occurring an event, age of any phenomenon, length of any product, and so on. For this kind of variable, we actually use the continuous probability distribution. If you see the definition of continuous random variable, it has an infinite number of possible values, and it can be represented in a number line, something like this one. So where we can define it as a hours spent studying before examination. So that's the hours or time points, you can say. That's the time spent studying, and it can be any number between 0 to 24 hours. And this is actually a continuous random variable example. So the distribution, or we can say the probability distribution for this continuous random variable, is known as continuous probability distribution. And obviously our random variable x is here continuous random variable, and in this particular example hours spent studying is our continuous random variable. Now you have already covered this discrete probability distribution like geometric, then binomial distribution, then Poisson distribution. In this lecture we are going to cover the normal distribution, and after that very briefly the exponential distribution. Both are continuous probability distribution. Now you can see that we have two different curves for two different type of probability distributions. The first one is for discrete probability distribution and the second one is for continuous probability distribution. Let's find out a little more about these curves. For any random variable x who has a value 1, 2, 3, 4 up to 5 has some defined probability. Like for x equal to 1 we have probability 0.1, for x equal to 2 we have 0.25, x equal to 3 0.3, and the summation of the probabilities of these possible x values will be or must be 1, or we can say 100%. So that's how you will get the total probability from a discrete probability distribution. And you can find one thing, that this gives us the height of a variable in terms of probability. So you can say the discrete probability distribution gives us height in terms of probability. But what about continuous probability distribution? They gives us the area. Like discrete probability distribution, they don't give us the height, they provide us the area, and we have to calculate the probability of this particular area. So that's the total area of a continuous probability distribution, and it must be equal to 1 or 100%. Now look at this histogram. If you can see closely, it's actually an area. You can say this is an density curve which has an area that's particularly covered by this diagram. Now if you plot a curve above this diagram, which is actually a symmetric curve, you can find out very easily the mean, median and mode all are equal. Now let's see how to calculate the probability for this kind of density curve. So we're taking the same graph like previous, and that's the area actually we have here. From the following density curve below, let's find out approximately what percentage of people weigh exactly 60 kg, or what is the probability that the people weigh exactly 60 kg. So that's our question here. And let's define the random variable. One of the most important thing for a probability distribution to define your random variable. Here our random variable is weight of a people, and as you know that weight is a continuous random variable, so this density curve must be belongs to a continuous probability distribution. Now, a common mistake that students make in this type of question is that when they see exactly 60, they put a line and then calculate the probability, which actually the way for discrete, but in continuous it will be 0, because in continuous we need to find the probability of the area, right? So here we can't get the probability, that's why it will be 0. We can't get the probability because we don't have an area here for this single line. In fact, the area of this line is equal to 0 because a line has no height. As a result, the answer is 0. Logically this makes sense, but realistically no one will ever weigh exactly 60.000 something kg. Usually you will have some measurements very close to it, like 60.5, 60.71, 60.05, 60.23, and so on and so forth. However, if I ask to find out the probability or the percentage of people weighed between 60 and 70 kg, then how can we calculate this one? The first thing we need to do to cover this area, and after that shade this region, and then calculate the probability using some integration or other formula for continuous probability distribution. So for this particular thing, the main message is that in continuous probability distribution, for a particular point or value, you can't find the probability, as you can't find the area here, as it has only the height, not width at all. So in continuous probability distribution, we must have to calculate the area within some range. So that's how you can find the probability of an area of any kind of density curve under this continuous probability distribution. In continuous probability distribution, you are going to have the density curve. You need to remember two things for density curve. A density curve must lie on or above the horizontal axis, and the total area under the curve is always 1 or 100%. When we talk about normal distributions, we refer to the data we get from a population or sample. So before we actually talk about the normal distribution, we need to first distinguish the difference between a parameter and a statistic. A parameter is a number that describes the data from a population, whereas a statistic is a number that describes the data from a sample. Examples of parameter and statistic are mean and standard deviation. Now for sample, we denoted the mean by x bar, and for population we denoted by mu, and for standard deviation S and sigma. So these are the statistic, and for population we are defined this as parameter. Now these two are the population parameters. Mu and sigma are very important when you talk about normally distributed populations. So what is a normally distribution anyways? If you ask enough people about the shoe size, you will find that your graph data shaped like a bell curve and can be described as normally distributed. A normal distribution is a special type of density curve that is bell shaped. For this reason, the normal distribution is sometimes called the bell curve or the normal curve. The distribution describes the tendency for data to cluster around a central value. In fact, this central value in the population mean mu, which is always located in the middle of the curve. So for any normal distribution, we can say that some data points will fall below the mean and some other data points fall above the mean. But most of the data values are located near the mean. It is widely used and even more widely abused actually. You see bell-shaped curve in almost all disciplines. Many of the different continuous variables use the nature of normal distribution because of its shape, like exam grade or IQ score, height, weight, blood pressure, volume, or even time to finish a task, and many more. It's a continuous random variable, as we said before. Like discrete probability distribution has probability mass function or PMF, continuous distribution variable has a probability density function, which actually its identity. And using this probability density function, you can calculate the probability of a particular area under the curve. Now here is the range of x is minus infinity to positive infinity. So the range of the mean is also minus infinity to positive infinity. But what about variance? Variance gives us how much it varies, more or less. So it can't be negative. That's why the variance must be greater than 0 up to a positive infinity value, and so the standard deviation. So we can say that x, the continuous random variable, will follow normal distribution with mean mu and variance sigma square. As it is a continuous function, we can find out the probability by integrating in a particular range. But as you can see, the form is a little bit complicated one, so we use a different method. So you can see that this is a table and there is some values. These are actually the probability values and these are our variable. So we don't need to integrate that complicated formula at all. We just need to find out the probability under this curve from using this table. For that we need to transform our random variable x into some standard normal variable z. Now here we have that x follow that normal with mu and sigma square. This mean and variance are the properties of this normal distribution, or you can say the characteristics of this normal distribution. And this population mean mu and the population variance sigma square, if you replace these two with 0 and 1, you can say that it will be follow a standard normal distribution z with mean 0 and variance 1. This normal distribution is also called Gaussian distribution or bell-shaped distribution. Bell-shaped because of this bell-shaped curve, and this is its mu, and that's the range it covers, both the random variable x and the population parameter mu. Now as we say that x follow normal distribution with population mean mu and variance sigma square, if you replace this mu with 0 and sigma square 1, then you can say a new variable z, which is our standard normal variable. Now look at this transformation where we have a new value z which has a mean 0 and variance 1. How to transform this one? What you need to do, if you have a value of random variable x, put this value and take the difference from the mean value of the population mean and then divided it by that corresponding standard deviation value. Then you will easily get that transformed standard normal variable z, and that z has a probability density function which is also being changed in some extent, and that's range is remains similar as we have our original random variable x. Then we can write that z, or we can say the standard normal variable z follow normal distribution with mean 0 and variance 1, and that's how the curve shows.